Hello folks, welcome back. Today we have another Standard Electric Time master clock. This was brought in by a viewer who wanted some service done on it. And I don't know anything about this clock, haven't been inside it yet, but we're going to evaluate the condition and we're going to make it run. Since I did such an exhaustive video series on refurbishing another one of these clocks, we won't go through the whole thing again here, but just wanted to see what's up with this one. This one has a white face, some of them are silver. This is also a 4-channel clock, and we know that because of the 4 bell buttons there, as well as the electrical contactor setup that's set for 4 items. The clock does appear to be complete. It was not running when the person brought it into me, but what I've done here is I've just stuck my hand behind the movement and I wound up the torsion drive spring, and that all feels intact. So we're just going to give it a little kick here and see what happens. We're a little out of beat, but it is actually running. One of the things the customer asked me to do was just evaluate the electrical condition of everything and then figure out what voltage it runs on. This clock, the joke about Standard Electric Time is that they weren't so standard. They did get made in a variety of voltages depending upon the circumstance. So we are going to go slowly and make sure that we don't overwhelm anything in the clock. But so far so good. So let's get the dial off and get some juice flowing and we'll see if we can make it go. The main concern when taking in a clock like this is if the coils have been burnt out, either due to some kind of electrical fault, wear, or somebody putting too much voltage on. That is really difficult to repair because you would have to, if the break isn't right on the edge, you'd have to actually rewind the coil, and that's pretty daunting. So what we're going to do is just do a basic resistance check of all of the coils in the clock. There are 6 of them. We've got the 4 bell relays. We have the main operational coil solenoid there, and then this is the slave one. So I'm going to just take my meter, and we expect some value that's less than infinity but more than 0. And I'm just looking on the winding side here. We got 200 ohms there, going around to all of these. That's a little bit less, but still sane. These are the terminals for the main movement advance. And go up here. Okay, so the good news is all of the coils appear to be good. And that means this clock should be repairable. With the dial off, I did try to run it, and it ran for a few seconds, and what we see right now here is it's no longer moving forward because of junk in the movement. It's getting bound up. So our first step is going to be mechanically cleaning this. We'll take it apart, ultrasonically clean it, polish the plates, and then once it's mechanically happy, then we'll look at the electrical side further. We've got the movement polished, and through the ultrasonic cleaner, I have polished the plates and lacquered them. And I'm just doing some test of the condition of the pivots of the clock. One thing I'm noticing here is this pivot has quite a bit of movement. So we need to put a bushing there. We'll take care of that. If we look on the back side, these are relatively good. A little bit of wear on the escape wheel. So we might get away with just one bushing here. A little bit of slop is necessary, but this is too much. So we're going to put a bushing there in the plate to take that slop out. One thing that you have to be careful of with bushings is to know where to put it. As we can see, this pivot moves left to right, and that was the wear pattern as the gear train ran. So we need to actually put the bushing in the original place. And I can know which way the clock wore by running the train in the same direction that it ran. So I've got my torsion spring here. So when we get the click in here, this is how the clock winds, by putting pressure on this spring, which means the train wants to drive this way. So as the clock is wearing, it's pulling that pivot off to the right. And what that tells me is I need to actually center my bushing on the left side of this hole in order to put the hole back to where it originally was when the clock didn't have this wear in it. For clocks that have square plates, I like to do bushing actually in my Bridgeport because it's a lot more rigid. Due to the odd size of this plate, I'm going to use the Bergeon machine to do this bushing. That lets me clamp in an arbitrary place, but this is not as rigid, so placement isn't quite as good. Here's our new bushing. That is still spinning freely. I've got good end shake, and our movement runs nice and easy. We can go ahead and finish putting this back together. When I first put the movement together, I had some trouble with a couple teeth on the escape wheel. You can see I marked one with a black Sharpie there, and there's another one coming around in a minute. And that was damage from a crash of the pallets or something like that. There's a second tool coming in on the left side. So to make this work, I ended up putting a bushing in on the escape wheel as well. I initially thought that was okay, but wanted to tighten that tolerance up to position the escape wheel a little bit better. And after some massaging of those couple teeth and a bushing, we are set from a mechanical standpoint when just manually wound here. So now it's time to wire it up and see if we can get it to run under electrical power. Here's the variable DC power supply I've showed on the channel before. This one can do 0 to 30 volts and 0 to 3 amps. And what is great about a device like this is you can set both a voltage output as well as a current limit. If we look on the screen here, right now it says I'm running at 21 volts. And right below this, I've set a limit of 0.35 amps. And what this means is that even if I have a dead short somewhere, there's not going to be enough current to actually break anything. What will happen is the voltage will just drop down to 0. And so I covered this in a lot more detail previously, but the intent of this is to find a safe voltage where the clock is content with what it has and it's not excessive, but there does need to be a little bit of margin as well. The settings that I have here right now, which is 21 volts and 350 milliamps, we did actually hit that limit, and if you look at this, you saw the voltage drop below the nominal 21 volts here, meaning that it did actually want that whole 350 milliamps to do it. Some voltage drop is acceptable, and 350 milliamps is a reasonable amount of current during a high current cycle of the clock. In about 5 or 6 seconds, again, we will see the current and voltage draw. We'll see what that looks like here. So we dropped to about 18 volts when we hit our 350 milliamp current limit there, and the clock was pretty happy at 21 volts. I still think this is probably like the other clocks I've done, a nominal 24 volt clock, and I've actually run this clock at 24 volts and it seems to be pretty happy there. Again, if you're testing a clock on your own, the main thing is to just have a power supply that you can control the current limit with. You do not want to stack up a couple car batteries here where you have essentially infinite current. That is a recipe for burning stuff up. An electronics power supply like this that works on the order of milliamps is really what you want to have. So I think we've established that this is a 24 volt clock, and we'll get a permanent supply that is in this range of 24 volts and probably 500 milliamps. I fixed this off camera, but did want to talk about one other mechanical thing that I did. This is the tape drive mechanism, and it has 2 levers here. This is the minute advance lever, and this actually advances 12 hours. And so you can see on the pins here, we've got Friday, a space between Friday and Saturday, Saturday, a space between Saturday and Sunday, etc. And you can see that the way that the pins are arranged, anytime there's a pin, it lifts the contacts off of this bar, which prevents the bells from ringing. And so right now, this clock does not ring anytime on Saturday or Sunday until we get to Monday, when these arms don't have a pin pushing them up. Now they're making electrical contact, and anytime the tape has a punched slot in it, that will trigger a bell. What I discovered is the minute advance was not reliable, and in looking at that more carefully, what happened was there was actually quite a bit of wear right in these pivots right here. This would move up and down, and that would prevent the solenoid from being able to pull the drum into its correct next minute position. So I ended up actually putting a bushing on the front and back of this, just as I did on the time movement. And now it's just as reliable as can be, just light pressure. It advances perfectly every time. So I think this is the end of the mechanical running. We figured out what we need electrically. I'm going to put the paper tape back on and the dial on, and we'll let this run for several days and make sure it's reliable for its new owner. Here's our clock running as expected. We're about to wind here. There we go. Dial and hands on. Tape mechanism fully working. There we go. I'm excited to get this back in the hands of its owner. Thanks for watching.